All right, so I guess you all got this handout. Yeah, I see some of you have it out. I'm going to sort of walk you through these notes on reinterpreting this limit theory and how it's used in mainly in information theory and hypothesis testing. So in a way, it's sort of a crash course on detection theory. There's a fun quote here, which, you know, a very excited author in economics wrote just, you know, a paragraph saying how Wald created everything in 1939, and some of the ideas here go back to the 1930s. I mean, in particular, this idea of an empirical distribution. So I'm going to recast these limit theorems in terms of empirical distributions, and I'm going to try to explain to you why that's so exciting and how it makes things simpler. It gives you a lot of intuition. So let me just start with that. I'm just going to use these notes as a guide. So the empirical, so basically the same set as before. I've got this IID sequence. It doesn't have to be. For now, it's just a stochastic process. We'll put in assumptions as we go along, but eventually it's going to be IID. So independent and identically distributed. And why? Because it's very easy to you know, give you very precise conclusions. Everything I'm going to say has generalizations to all sorts of different settings, but we want to keep it simple. So what's the empirical distribution? It's a probability. It's a random probability measure. Okay. So the nth empirical distribution pi m, it's a stochastic process itself. So for each m, I have a stochastic process, but it's a probability mass function. It's a random probability mass function. Okay, so that's the language Hayek uses in his book, probability mass function for a discrete probability measure. And it's just defined as follows, you know, pi m of any set A is equal to 1 over m, sum k equals 1 to m, indicate a function that xk is an A. All right, big deal. So you basically look at, for any set A. Okay, we'll restrict to the Borel sigma algebra in R. We don't need to. For any set A, there's the definition. Okay, we don't need anything fancy at this point. So you could also say, you know, pi m is an average of Dirac delta functions. Put a dot there just to emphasize that. This is exactly the same as saying that. That you look at the observations of the stochastic process, the first m observations, and then you look at this average of the delta functions there, and it turns out this is a very, very useful definition, and I'll illustrate that over, I guess, 4 hours. This lecture, Tuesday, Wednesday, we're going to mainly be talking about empirical distributions, and one thing that's useful is when you integrate something. Suppose I want to take the expectation of a function with respect to this empirical distribution. So I want to integrate some function f of x pi m of dx. So here's notation I realized I haven't introduced before. But if I have a pi m doesn't have to be empirical distribution. It could be have a density. It could be mixture. It could be discrete. Whatever. If I have a probability law, this is standard notation for integrating any function with respect to that. You know, so this is a random probability. For every omega, this is a probability measure. You can see that. For any omega, xk is just a bunch of numbers, and we're looking at a discrete probability measure on those points. This is notation you should just learn for any probability measure. We have this. Okay, it's just notation. I think it's hard. I'm scared to say expectation because pi m is already random. Let me just write it down over here. In general, if x has distribution mu, all right, I can write down the expectation of x as equal to the integral of little x mu of dx. That's notation we'll use all the time. Okay, and that's also equal to the integral of x df of x, where f is the CDF. All right, and f and mu are related somehow. So what is forget it. So yeah, f. What is it? Yeah, what is f of c in terms of mu? Mu is a probability measure. So remember what that is. It's the probability that x is less than or equal to c. How does it relate to mu? It's easier than that. You could write as an integral, but it's just mu of something, right?
Mu of x less than?
Yeah, you got it. You could write it like that too, but I'll just write this. It's mu of this event. Yeah. All right. Okay, so mu of a is between 0 and 1. There's a long distraction. So a probability measure is defined on the Brill sigma algebra, and you know it's a probability measure. So this is between 0 and 1, and the CDF is just defined to be that. But anyway, this is notation that's really, really common. Okay, and it's sort of intuitive, right? I mean, it's sort of like you're looking at the probability that you're in a little interval, and you're summing over all the intervals. Yeah. Okay, but so that's a random variable now when I integrate this. And what is it? So while I was rambling over there, did anybody work out what this is? Well, how do you take the mean of a discrete random variable? Right?
Sum of all the values and multiply by their point mass probability.
Yeah, and it's all uniform. You know, it's 1 over m there. So all the weightings are all 1 over m. So it's just 1 over m. Sum k equals 1 to m of f of xk. So when I say you can, I talk about empirical distributions in limit theory, well, there it is. All the limit theorems I talked about in the last lectures was about looking at this averages like that, right? And all that is a dot product between f and pi on the left-hand side.
Can we not say that is the expectation of, this expectation of f of x?
No, it's the empirical mean of f. It's a language that's used like in, you call this the empirical mean, And we know by the law of large numbers that the empirical mean converges to the actual true mean, if x is IID, x is IID. Right? But you see the beauty here. So, I don't know if it's beautiful yet, but on the right-hand side, I've got f, which is some horrible discontinuous nonlinear function, possibly, right? And I've got f of xk and averaging over here. Here, it's all linear. I'm to have a dot product, this is a linear operation over here. And so it's a typical thing you do is that you've got x that lives here in the real line, a one-dimensional object, and things are complicated over here. I've got f of x, which is complicated. F is some 100th order polynomial, I don't know. But on the left-hand side, I have a linear operation. It's a dot product. But I'm in infinite dimensional space, basically, because pi_m is in the space of probability measures, which is some infinite dimensional space. So standard thing that happens all the time, you go to a high dimension to get linearity. It's just, it's a message that's just a theme in optimization, in the systems areas. Okay. All right. So we know that this converges. We know the strong law of large numbers holds. So if this mean exists, then but the strong law of large numbers says that this will converge to this in the almost sure sense. And you can actually strengthen this a little bit more. So that's the first thing I'll just mention. And there's an eraser somewhere. Is it back there? There's a slight mistake in those notes I discovered this morning. So, in the notes I write, basically theorem. It's a proposition. Did I call it pi_m over there? I did. Hold on a second, just let me finish writing this down and then I'll answer a question. Yes, I said there's a mistake in the notation here, which I'll get to, and yes, what's your question?
What is converging almost surely to the expected value of f of x mean?
No, I just meant this. Yeah, I meant that this average, we know that the average, see if xk is IID, then f of xk is IID. And the law of large numbers says that the average converges to the mean and then goes to infinity. I put a 1 there, I could have put a 25. I said it's IID, so again, I'll put a 12 there. It doesn't depend on the index. Remember, IID means independent and identically distributed, so the time index here doesn't matter. All right. So that was, I said that to you last time. That's actually a hard result to prove. The strong law of numbers is not trivial. Take an analysis course. I'm not gonna prove that. The CLT trivial. It's a one-liner. You could do it all in your sleep. And the law of large numbers is deep. Okay. Now, what's fishy here is that last lecture I talked about 4 different kinds of convergence, in probability and distribution, almost surely. I had an LDP, and it was all about random variables. And I write this now. There's 2 notions of what I mean by convergence and distribution, so I should go back and just give you a clarification. Right, I want to like this. So the first definition of convergence and distribution was I look at the CDFs. And they're supposed to converge pointwise for every C at which this is continuous. So ignore the jump points. All right? But if these guys each have, you use the same notation for their probability measures. Okay, so mu n is a probability measure associated with the distribution, the CDF. And so you see these are deterministic objects. I'm just looking at the probability measure associated with Cn converges in distribution mu. It's the same as this, okay? So it means the associated CDFs converge. And that's equivalent, remember, is saying that the integral with bounded continuous functions converges. Okay, and that's the same as look at the characteristic functions. All right, so that's a theorem I stated last time without proof, that this is equivalent to this, which is equivalent to that. All right, but here I'm just writing in terms of the probability measures instead of the CDFs. Big deal. All right, so see you last lecture. But so you see there's a real problem. And so first of all, clarification. I hope you all get it. You use the same notation for the random variables or the underlying probability measures. You just use this notation. Okay. But you see a real problem with this sort of result, because to check for this property, you have to check for every single continuous function, there's a lot of them, or forget that, for every real number u, I've got to go and check something. It's very doubtful that what we're talking about is an event, you know, because we have an uncountable intersection. For every u, we want this limit to hold. That's an event. All right, event, this convergence takes place. So so the mu n is now the pi ends, they're random. And so an event that this converges, and I have to take the intersection over all possible u's, that's an uncountable intersection, dead. All right, this.
I'm trying to pick apart convergence in D and almost sure.
This is a probability measure, but it's random.
So the sticky point is because the convergence in D said that the events, right, don't have to come from the same event class, like over time.
No, there's only one event. Whenever I talk about the real line, it's the Borel signal algebra.
Yeah, but the almost sure convergence said you have the same probability space for all time.
I do, yeah.
But
right.
The convergence in D said you don't. All the events don't have to come from the same probability space.
No, I said it can, but here they are.
They are?
Oh, yeah, no, here we have, no, take a look. I've got a stochastic process, right? And from the stochastic process, I get the empirical distributions. And my claim is that those converge in distributions. So everything's nailed down one probability space. That's not the issue. Yeah, so you're thinking ahead. No, that's not the issue. The issue is that this is an event. If these guys are now random, mu n's is the pi n's. This is an event. I want that to hold for every u. It means I'm taking an intersection of event u over an uncountable number of u. All right. So that looks like it's trouble, but it turns out, thank God, one can prove this, okay? Take an analysis course. It turns out that for this to converge for every u, is the same as a converging for all rational u. There's a countable number of rational functions, and so there's only a countable number of restrictions. The intersection of a countable number of events is an event. So we can, you know, so this is one solid ground, right? And there you have it, you see. So the proof of the proposition then is done. I mean, right? So okay, so I'm going to take f of x where the law of large numbers. Okay, so I know this converges to the mean almost surely whenever the mean exists. If I let AK equal the set of omega such that, let's just do it, you know. So I'm taking f to be this complex function of x, and I'm letting a be a set of ak such that this, a set of omega such that this limit holds. Where's the omega? That's deterministic. That's a number. That's 25. Or it's complex. It's 25 plus 2j. I don't know. F, that's not random. It's just a function of x. So it must be there. So that, remember, that's a random probability measure. You know, so the omega is hiding there. All right. So that's an event. You know, we've discussed that last time, why that's an event. And the probability of AK equals 1. And I claim that therefore the probability of the intersection k equals 1 to infinity of AK is also equal to 1. And last lecture I said, Jesus, I can't think of a two-line proof of that. And an alert student came up to me after class and said, it's a one-line proof of that. It's very, very simple. And I'm not going to prove it. I'm still not going to prove it. But it comes from axiom 3 of the definitions of probabilities. Okay, so we have a bunch of events, each of which have probability 1. Their intersection also has probability 1. I may give it in the homework. It's actually in the notes. It's actually in those notes. Okay, but that's it. And so that's it. That's the same as saying the result. That's what I'm saying right here. Yeah. So there's not much to that. I mean, this is just, you know, playing around with the definitions. All right. This is not the thing I'm excited about. It's just, I mean, the only thing exciting to me here is that you can go from something nonlinear, an average of f of xk, to something linear, pi m dot f, a linear operation, and that's useful. All right. Okay, so let's get to something meatier that actually leads to something deeper. I'm just going to be able to set things up here. And what do I want to say? There's so many things I want to say. I could go crazy. But So what's my notation? So I've been using, I don't like that px. I took that from Hayek's notes. It's ugly as hell. I use something different here. I changed it to p. So a little p is going to be, is going to be my distribution for xk. And so what I'm saying now is I've got my little p sitting there, and I have, my little guys over here, pi m's, which are floating around. But as m gets larger and larger, say 2,000, we start getting closer and closer and closer. All right? But the thing you ask in large deviations is what happens, maybe it takes a long time. What happens if, what's the probability of being far, far away from p at some given time? And I want to give you some geometric way of thinking about this. So I'm going to be looking at things like this a lot, so let's get some notation. And for some reason I switched to A here instead of C. Last lecture had a C. I'm going to call it A now. What was the notation I used? All right. Okay. All right. So, in the sense made precise last lecture, for large n, we have this approximation. That looks pretty meaningless because that's going to 0, that's going to 0. Yeah, 0 is close to 0. But remember what I said was I take this quantity, I take its log, I divide by n, and I converge to that, minus that rate function. So look at your notes from last time. All right. So this is this average of these functions. But remember, this is just pi n dotted with f. I've got a dot product. I'm looking at a half space. So I need another color pen.
Dr. Ryan, you said what space are you looking at?
It's a half space. So I've got so here this is a set of all probability measures. So I could call it, sometimes people write this as this whiteboard right now. This part of the whiteboard is the set of all probability measures on R, say, and P is what's special about these PMs is that they're discrete random variables. They're probability mass associated with probability mass functions. P could be anything. It could have a density or a discrete or anything you like. But when I'm looking at this event, it's a half space constraint in the space of probability measures because it says that P dot F is greater than equal to A. So this the picture we're going to exploit is that, oh, damn, I needed this red pen. I don't have a red pen. Oh man, green. Okay, I could live with green. Thank you. Green's okay. It's all Christmassy. So this line, this area here, is a set of all. Oh, forget it. Whoa, nice. All right, we're back to red. This is the set of all, say, mu, such that mu dot f is greater or equal to A. Okay, so the set of probability measures is a convex thing, but forget that. Just think of it, think of it as Euclidean. Let's just forget the fact that probability measures are non-negative and they sum to 1 or integrate to 1. So we're really in a convex set, but forget that. So we've got a half space constraint. We've got a half space plus the fact that it's positive and integrates to 1, and we're interested in, so this question, the LDP question, so this thing that was supposed to be red, I'm calling that HA. Maybe we could try to make it red. Oh yeah, it is okay. The set of all probability measures whose mean, where the mean of f is greater or equal to A, is like a half space, and we're asking, is the probability empirical distribution in that half space? And so there are all sorts of questions you can ask. You could say, given this weird thing happened, like n is really large, you'd think by now the thing would have settled down and pi n would be near p. In fact, it's not. You're way out here. Where is it then? You can, turns out you can nail that question. There's only one place it can be. And I'm going to tell you exactly where it is. It is right there. Exactly. I'm going to, so unfortunately not today, but by midway through the next lecture, you will know that in this rare event that the empirical distributions are in this half space, they must be there. And so you can get some really nice tight results on, given a bad thing happened, what other bad things happen. And you can it's amazing how strong it is. And you can really see it in simulations, and it's very, very precise theory. And again, like I said, it's the basis of rate distortion theory, channel coding, hypothesis testing, all the geometry, it's right there. So we can do all that in 3 hours. And this is just the warm-up. Okay. So, yeah. Cool. And yeah, so that's the objective, is to get to that. And of course, we'd like to ask other questions. So why we stick to half spaces? Why not look at a set like that, a set B, and figure out like what's the probability of being out of this blob when I should have been over here, And you get a formula for it for any set, any blob you want, and you could say the same thing, that given this weird thing happened, that M is very, very large, and I'm actually in this set here, I can tell you exactly where you are. It's overwhelmingly likely that you're going to be at some point here. So given that you're in this big blob, you must be there with extremely high probability, and you can compute that location. Right? And then again, I will explain how that leads to the formula for capacity of a communication channel and things like that. We can nail that. if you want to. If you don't want to, we can do something else. But this geometry I do want to get to you. So in order to come up with that, in order to understand how to get a better appreciation of the large deviation principle and to understand these more general questions, there's two things you need to understand: entropy and relative entropy. Okay, that's where this all comes from. So entropy pops up all over the place here. So you think these moment generation functions are so fundamental, forget it, they're not. It's relative entropy that's fundamental here. And it's absolutely amazing how it pops up. You know, it's just, it's wild. Okay. And you're all cheating. I shouldn't give you the notes in advance. You're all cheating. You're ahead of me. And I wrote it as a sum. Let's not do that. Well, I guess we do for entropy. So entropy is really annoying. So okay, so you're forced to do this. You're forced to go to discrete random variables when you talk about entropy. There's something called entropy. There's an entropy rate and so forth for continuous, but it gets ugly. So that's